Okay, can you hear me? Come on, say something.
Yes, Prof.
Oh, great. All right. So today is lecture 5. Sorry about this, but there's no LT7.
Yes, Prof.
Oh, okay, great. So today we are going to talk about, we're going to review the last part of the lecture from last time. And then we're going to start with discrete random variables. Okay, so you are required to read section 1.6 here and section 2.1 here. This is a compulsory reading. All right. So now we will start with reviewing K permutations and K combinations. And the story is as follows. Okay. So we have n objects, right? N objects. And we would like to select a bunch of objects in the study of K permutations. And we have to put them in a sequence. Okay. So the idea is, the question then is, how many ways are there of selecting these K objects out of n and putting them in a row? Okay, so right, so let's just look at say example K equals to 1. Okay, and we have a total of n objects, and we need to put one out of the n objects in a row, but there's no row. Okay, so you have n objects in total that can come into this bucket or this bin here. Now in the other extreme case, all right, if K is equal to n, of course the K you can only be from 1 to n. It cannot be less than 1 or more than n. So if K equals to n, we have a total of n buckets or bins. Okay, what I'm saying is buckets. Okay, so in the first bucket, we can place a total of n objects, 1 out of n objects. Then after you have selected one of the objects, then you have to select from the remaining n minus 1 objects. So for example, if these are the objects here, and you have selected this guy to go inside here, right? You have selected this guy to go inside here. Okay, now you initially started off with 6 objects, so n is equal to 6. Then how many objects do you have left? Well, you have this object, this, and this. So you have n minus 1 objects left, right? So n minus 1 objects can come here. So suppose you have selected this object to come into this bucket here. Then how many objects do you have left? Well, you have n minus 2 objects left. Okay. Then suppose you selected this object. Okay, you selected this object in this round here, and then you put it inside here. Then you have only 3 objects left. So clearly you can see the whole principle here, and you're left with this 2 and this 1. And so this is actually has a name. This number of permutations actually have a name. This is n times n minus 1 times n minus 2 all the way times 2 times 1. This is called n factorial. Okay, and this is terms n factorial. So n factorial, this formula you need to know, and you need to know it very well. In the general case, now you can see that if K is between 1 and n, then the total number of ways, to select K objects out of n and put them in a sequence, put them in an ordered is important, sequence is actually n times n minus 1 times n minus 2 all the way until n minus k plus 1. All right, it's not n minus k. All right, if it's n minus k here, then what you have is that you already have k plus 1 terms. So this is n minus k plus 1. Okay, this is important for some sort of small bookkeeping. But you notice that this is equal to n times n minus 1 all the way down to n minus k plus 1, n minus k dot 2 times 1 divided by n minus k minus 1 dot 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 2 times 1. So a lot of things here cancel. The 1 cancel, the 2 cancel, this cancels with this, and this cancels with this. All right, so you can see that what I've done is not incorrect, it's actually correct. But we can actually write this in a more convenient way, n factorial over n minus k factorial. Okay, because the top here, the numerator here is actually n factorial. And the denominator here is actually n minus k factorial. So you see this notation quite often. Some books write, but we will not write MPK, but it doesn't really matter. Okay, but feel free to ask me if you have any questions, okay, in the chat or unmute yourself. Okay, so last time I went through one example. Now I will try to go through another example. Okay, so this is example 1.29 in the book. So you have N1 CDs of type, of type 1, and you have N2 CDs of type 2, okay, and you have N3 CDs of type 3. So I go through these examples in the book so that you can revise them on your own, okay, when you read the book. So we want to arrange these CDs in a row in order so that the CDs of the same type are contiguous. All right. Arrange the N1 plus N2 plus N3 CDs in an ordered sequence. So the order matters, such that CDs of the same type are contiguous. Contiguous means together. Okay, so we can have the following. We can have type 1, type 1, type 1. Say we have 3 type 1, but here we have type 3. They must be contiguous, and type 2. This is one arrangement. But each CD is different. So this CD is different from this, even though they have the same type. So for example, this is rock CD. This is a classic, and I don't know what else. Okay, so this is one arrangement, and I'm just illustrating here contiguity. So it is contiguous here. Can you see? So the contiguous, basically, you cannot have the situation that you are 1, 3, 1. That 1 is no longer contiguous, right? That is not allowed. So we need to count the total number of ways to do this. Now, one thing to notice here is the following. All right. Suppose I worry only about CDs of type 1. Okay, how many ways are there to arrange them in a sequence? So there are, as you know, N1 factorial ways to arrange these CDs, this type. Maybe I say this type of CD in a row in an ordered sequence. Definitely, right? So clearly I can do this for each one of the types of the CDs, right? So for CDs of type 2, right, then there are N2 factorial ways. N2 factorial ways. And for type 3, I can do exactly the same thing. And it won't be a surprise to you if there are N3 factorial ways to arrange this third type of CD in a sequence. So the total number of ways seems to be N1 factorial times N2 factorial times N3 factorial. But here I have missed out on something. What have I missed out on? Now, you could place your type 1 CD here, type 2 CD here, and type 3 CD here. 1, 2, 3. Okay, they are all contiguous. Yes. Liao Xue, now I know your name already. Okay, so but you could put the number 3 here, and number 2 here, and number 1 here. Okay, and how many ways are there of arranging these 3 types of CDs? Well, there are 3 factorial ways here. Can you see? There are 3 factorial ways. So this is the final answer, and it's correct because the 3 factorial accounts for, what does it account for? Number of ways to arrange the CD types in a row. Okay, that is 3 factorial. And here there are 6 ways. We can enumerate them. We can enumerate them quite easily. 1, 2, 3. This is 1. And 3, 2, 1. 1, 3, 2. 3, 1, 2. 2, 1, 3. And 2, 3, 1. These are 6 ways altogether. Now, for such a small instance, right, we can enumerate, no problem. Okay? Okay. Any questions? Samuel? So this is one of the problems in the book. There is another part to this, but it's essentially the same, so I will not go through it. Okay? Ken? Sorry, so Thursday we will go back to the lecture theater, hopefully. Liao Xue, any questions? Okay, good. I also know that there is some other student, later we'll call on him or her. Okay, so last time I also talked about K combinations. In a sense, this is a bit easier. Okay, so here again, we have n objects and we want to select K objects out of n. All right, so we are just selecting. So we have n people, n students all together, and want to form a committee of, say, 5 people in the committee. How many ways? Okay, and here I will not belabor the point because I explained this last time. So what happens here is that you will have this number of ways, which is n. This is read as n choose k. This is what we say, n choose k. And that is nothing but n factorial divided by n minus k factorial, okay? Now, relating this to the above, right? Relating this to the above is nothing but npk divided by k factorial, okay? So this is a little bit complicated the way the first time you see it, but this is nothing but selecting a subset of size k out of a subset or out of a big set of size n. All right. So now you can see that you can see why there's the inclusion of this term here. Okay. The reason is because for every particular permutation, there are a total of k factorial combinations. So we need to take this away. I think I've already illustrated this using a particular example last time where we selected 2 letters out of 4 letters. Okay, so I will not belabor the point. I will not mention this again. Okay, if you do not know, please review the notes from last time. But what I will do is I will do a particular example that is not in the book. Okay, I'll do a particular example that's not in the book and it's not typed out. So if you want to copy, please do. All right, example. Okay. So here we have the following example in a group of 6 boys and 4 girls. Okay, 4 children. I'll say in a group of, let's say, more people. Okay, 7 boys and 6 girls. 5 children are to be selected. Okay, and such that there are at least 3 boys. How many ways can this be done? Okay, so this is the question. All right, this is the question. So we have 7 boys and 6 girls. So we can illustrate this using this particular picture here. So 1, 2, 3, 4, 5, 6, 7. So these are the boys and 6 girls. 6, 1, 2, 3, 4, 5, 6. Okay, and we need to select 5 children. 1, 2, 3, 4, 5. Such that there are at least 3 boys. Okay, so here we need boy, boy, boy. But the word here is at least. At least doesn't mean exactly. At least means at least. That means 3, 4, or 5. Okay. So we can have this particular configuration where we selected at least exactly 3 boys. Then we need to select girl, girl here. You agree? So this is one configuration, one situation where there are 3 boys and 2 girls. But we could also have the situation. What other situations could we have? Well, we could consider, we could consider having more boys because we are allowed to have 4 boys or 5 boys. Can you see? Understood? So suppose we have exactly 3 boys here, exactly. Then how many ways are there of selecting this committee of 5 people with exactly 3 boys and 2 girls? Okay, so these 3 must come from here. These 2 must come from here, right? So any suggestions? So I'm just looking at this committee with 3 boys and 2 girls. Come on, someone. Let me call on someone. Oh, is David here? Come on, someone can give me an answer, right? Trina? Nope. So let's just focus first on this particular situation where there are 3 boys and 2 girls. Okay, 3 boys, 2 girls. How many ways are there of selecting 3 boys, 2 girls from 7 boys and 6 girls? Well, now I look at the 3 boys and I look at how many choices I have from the boys here. Well, I have to select 3 boys out of 7. So 7 choose 3. Oh, 6C2. Yes, times 6 choose 2. And these come from the girls' side. Thank you very much. Okay. Long Dengjie. I don't really know whether that's correct. You just give me 2 answers that are identical. No. Actually here, okay, thanks for the many answers, but here I'm just interested in forming a committee. I'm not interested in order. Not interested in order. Okay. So actually this answer that Xiao Xue gave me is actually correct. And it's different from your answer, which means that your answer is not quite correct. Okay. So if I'm going to expand this in more detail, okay. So this is equal to how much? 7 factorial over 3 factorial, 4 factorial, 6 factorial over 2 factorial, 4 factorial, which is a bit different from your answer. Okay. So here I'm not interested in order. I'm just interested in how many ways can this be done. Okay. So we are talking about a combination question, not a permutation question. Hopefully you appreciate this. Deng Jie, you understand? So what you are giving me is the P version. I'm interested in the C version. Okay, very good. So here, now we have 4 boys and 1 girl. Here we have 5 boys altogether and 0 girls. Okay, so how many combinations do I have here? Here I need 7 and I need to choose 4, right? Here I have 6, I need to choose 1. So this is whatever it is, you can plug into the formula. This part is the same. 3 factorial, 4 factorial, 6 factorial over 5 factorial, 1 factorial. Okay, so here, well, we have 7 boys at the beginning, but we want to choose 1 committee full of only boys. So here we have 7, choose 5. But for the girls part, we are going to choose 0. Do you know what is 6 choose 0? Well, I'm going to tell you soon. So this is 7 factorial over 2 factorial, 5 factorial. Okay, then we have 6 factorial over 6 factorial, 0 factorial. You might think that 0 factorial is equal to 0, but it is not. Yes, 0 factorial is 1. Okay, so this is actually 1. This is 1. So 6 factorial, 6 factorial, this is 1. And obviously, now, if you are not going to choose any girls, there's only one way of doing so, which is not choosing any girls. So that actually explains the fact that you're not choosing any girls from the available 6 girls. Understand? Understood? Okay. So I'm not going to press calculator. I'm not going to press calculator, but you sum up all these things here. You sum up all this, all right, plus this, okay, this is all times, okay. Then with any luck, you can press the calculator correctly and you will get, hopefully, 756. You can go and check that, okay, but the answer is not so important. The important thing is you know how you get all these intermediate answers, all right, because I'm not going to test you on how you're going to press your calculator. I want you to understand how to get all these numbers from the story. And the story here is that, okay, it's a bit tricky because we have this word at least, okay? And in mathematics, at least means greater than equal to 3, okay? And greater than equal to 3, less than equal to 5 means 3, 4, 5, okay? Which is reflected here, 3, 4, 5. So you need to have 2, 1, 0 girls here. Understand? Understood? All right. Fu Fang Kang, understand? Cool. Right. So this actually concludes our discussion of chapter 1. All right. And you should now be all equipped to do all the problems in the first homework, which is due before the Chinese New Year break. Okay. Right. If you want to ask me any questions, you can ask me. No problem. I can help you with the homework. I've already done all of it. Seems to be manageable. And some people say it's too easy. So next time it will be more difficult. Okay. So we have actually completed chapter 1, which is the foundational chapter. And now to go to the start of chapter 2. As I mentioned, today we will start with discrete random variables and some probability mass functions. Okay. So this is the start of chapter 2 of the Bertsekas book. And we will talk about discrete random variables. So you're reading here, you have to read section 2.1 to 2.2. We won't be able to go through all of 2.2. Okay, hang on. Okay. Thank you, Xiao Xue, for being the co-lecturer here. But yes, so Samuel, let me address your question here. This is a good question, okay? Let me put it here. Okay, so here's a fact. Among given, let's say given n objects, the number of permutations is exactly n factorial. Okay, so that's one fact. Okay, another fact is the following: given n objects and some number k between 1 to n. So that means an integer. K 1, 2, 3, all the way up to n. This is my notation for k mean 1 to n. Okay. All right. The number of ways to choose to select k objects out of n and put them in a ordered sequence. Okay, I'm running out of space. Put them in an ordered sequence. Sorry. Is actually n factorial over n minus k factorial, which is npk. All right. So the Samuel, we don't try to remember formula. We need to try to remember. Okay, we need to try to remember what? The story. Okay, so this fact here is more general than this fact. All right, why is that so? Let me try to explain. Now, here you are given n objects and you want to select a smaller number of objects and place them in a particular ordered sequence. And this is the number of permutations. Okay, now, what is this? This is actually a simpler fact. Why? Because here what I'm in the first fact, all right, I am actually selecting n objects out of n objects. All right, I'm selecting n objects out of n objects. So I'm running out of space here, but n objects out of n objects. And then we have this formula here, n factorial, right? Then you may be wondering whether the formula is actually correct. Okay, in the sense that, okay, if I select n objects out of n objects and I plug it into the permutation formula here, is it correct? So let me do npn, all right, for Samuel. Now, for Samuel here, what is npn? It is nothing but n factorial divided by n minus n factorial, which is n factorial over 0 factorial. But one of your colleagues just now has already mentioned that 0 factorial is 1. So this is n factorial. So you can see that this answer here, n factorial, is the same as this answer here. So Samuel, do you understand now? Do you understand the situation? Samuel? So we don't remember the formula. We need to understand the story behind the formula. So the story here is, given n objects, we'll select k objects out of the n and put them in an ordered sequence. Okay, ordered sequence. But you see here, we are taking n. Yes, Samuel, yes. Fact 1 is n of n. Fact 2 is k out of n, but the k is general. It can go from 1 all the way to n. So fact 1 is a special case. In math, we say it's a special case of fact 2. Because if you know fact 2 and you are smart enough to specialize the k to n, you know fact 1. Understand? Okay, very good. So in math, we consider simple case and then we consider more complicated case. But in the more complicated case, it must corroborate the simple case. That means if you put the n in k to be n and you don't recover this formula here, something is very wrong with your theory, right? Yeah. So we cannot have that. Everything must be beautifully consistent. Okay. Right. Now I want to go on to random variables and discrete random variables. So you can, maybe in your previous JC or Poly, right, you have actually encountered discrete random variables or continuous random variables before. But the way that you were taught may be quite different from the way I'm going to teach. But nevertheless, it is not difficult. Okay. So a random variable X is nothing but a mapping from the sample space to the real line. Now, this may be a little bit difficult for you to understand, but so let me draw the sample space here. This is omega, and this is our sample space. So there are many points inside here. So for example, if the sample space is that of a dice roll, then this could be 1, 2, 3, 4, 5, 6, etc., etc. You know what's the sample space now. But a random variable is something that maps you from the sample space to the real line. So for example, if I got 1, I may get $1. Okay, maybe if I map to 1, I get $1. All right. But if my outcome is 2, I may get $2, etc., etc. Okay. Now, in a more complicated example, let's consider the sample space, which is a pair of dice roll. Okay. And now the dice is only 4-sided. Okay. So what are the possible outcomes? Well, we can represent them in a matrix. Okay. Now this matrix here basically is like this. Okay. 1, 2, 3, 4, and 1, 2, 3, 4. So every coordinate here represents a particular outcome. All right. So this is the coordinate 3, 2, which means that the outcome first dice is equal to 3, second row is equal to 2. Okay. So in another situation here, all right, 4, 4. So the first dice is 4, and the second dice is equal to 4 also. Okay. So this is basically now our sample space. All right, our sample space. All right. So this sample space is unlike that of just a single dice roll with 6 outcomes. This is actually a matrix, but now we can define a random variable. Here, define a random variable, which is basically a mapping from the sample space to the real line. And our random variable here is quite special. Our random variable x denotes the maximum of the 2 rows. Okay. So for example, if my outcome is here, then what is the random variable's outcome? All right, it is at 4 because the maximum is 4. Here we map to 3. Okay, because the maximum is 3. Now let's do another example. Now we are at here. Here the coordinate is 2, 3. Where do we map to? Well, we map to again 3. Okay, so that is the action of the random variable. Okay, it is nothing but a function that assigns a numeric value to each possible outcome of the experiment. Okay, so if the outcome is say 4, 2, then we will map to 4. All right, so for example here, we will again, the maximum is 4, we will map to 4. So you can see that actually different outcomes here map to the same value of the random variable. Okay, you could have that, or you could be distinct. For example, here, number 1 could map to number 1, number 2 could map to number 2, number 6 could map to number 6, etc. Okay, so that is basically a random variable. Okay, but this way of defining random variables may be a bit abstract to you, but nevertheless, it is some way of describing a random variable. Okay, so just to summarize, a discrete random variable is a real valued function. A real value function from the sample space to the real line. From the sample space omega to the real line. Real line means real numbers. Okay, so a random variable in our context is definitely a real valued random variable. Okay, a random variable can only take on real numbers. Okay, now we are in this chapter interested in discrete random variables. Okay, so RV stands for random variable. Okay, a discrete random variable has an associated what we call probability mass function. Probability mass function, okay, which I will describe very shortly. It's abbreviated PMF. All right, PMF is probability mass function, and this is not a difficult object. I will describe what is the probability mass function very soon. Okay, so a random variable in our convention, a random variable is always going to be uppercase. That means capital letter. For example, X, Y, Z. Now, the values that it takes on, is always lowercase. This is our convention and the convention of the book. Now, any other convention is wrong. All right, so we have to be very strict with this convention because we do not know what is a random variable and what is not a random variable if you don't follow the convention. All right, so I want to emphasize that random variables are always uppercase and the values that they take on, which are real numbers, are lowercase. So these quantities here are actually real numbers. This is the set of all real numbers in my notation. Set of real numbers. Okay, so now let me try to illustrate. What we really mean by a random variable. Okay, so let X be the number of heads we get in 2 tosses of a fair coin. All right, so for a fair coin, we know that the probability of the event heads is equal to probability of the event tails is equal to half. All right, so let us try to describe what is the probability mass function for this particular experiment. X, recall, is the number of heads we get in 2 tosses of a fair coin. So now the first thing you ask yourself is X a random variable? X must map the sample space to the real line. Okay. So what are the values that X can take on? Now, if we toss a coin 2 times, then what are the number of heads that we can get? We can get either 1 head, 0 heads, 1 heads, or 2 heads. So indeed, X takes on real values. It must take on real values, cannot be complex, cannot be anything else. So this looks like a particular random variable because the X here, the uppercase X, can only take on real values here. Okay, so it's allowable. So now, let us consider, for example, okay, the probability mass function of X. Now, this is not so simple. Probability mass function of X. Okay, so what is the probability mass function? The probability mass function is denoted as little p, capital X, and little x. So I want to remind you, I want to drive this home that this is uppercase, and these are lowercase, little p, little x, lowercase. And we use this notation to denote the probability of capital X taking on the value little x. And here the little x can only take on 3 values, x equals to 0, 1, and 2. Okay. And in this particular case, as you know, little x can only take on 0, 1, and 2. And if x is equal to 0, x is equal to 1, x is equal to 2, let us figure out what are these numbers. Now here we have how many heads? Only 0 heads. So we have the outcome TT, tails, tails, because we don't have any heads, right? So in the other extreme scenario, we have 2 heads. So the only possible outcomes are HH. And the total, the sample space here is actually tails, 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 heads. The order matters, heads, tails, and heads, heads, right? So this is the sample space. So if you have 1 head, then which are the elements that you collect? It's basically this and that, right? So we are going to collect this tails, heads, and heads, tails together into our set because there's 1 head here. All right, head, head, and that is 1. Okay, and here we have 2 heads and x is equal to 2. Can you see that? So we can actually compute the probabilities here. It's not very difficult. So that's what we will do. And this is our first example of our probability mass function. Okay, so that's px of x. So what is the chance that we have tail, tails? All right, it's 1/2 times 1/2, right? And the same thing is for heads, heads. All right, it's 1/2 times 1/2. And of course, it's 1/4. I'll just put on 1/4. And the remaining one, you can actually compute the probability, or you know that the probability mass function must add up to 1. So this is actually half. Okay, so this is 2 times half because the probability of this is 1/4 and the probability of this is 1/4. Okay, yeah, 1/4, 1/4, so it adds up to half. All right, right. So maybe it's better to write this as 1/4 plus 1/4. 1/4 plus 1/4 equals to half. And you need to check that. You need to check that these add up to 1. All right, these definitely add up to 1. So what we have here for a valid probability mass function, okay, note that any valid PMF must satisfy 2 things. Number 1, that these values are all non-negative. Okay, so it's non-negative because probabilities cannot be negative. So this is all for all x in let's say the values that x takes on, capital X takes on. So in this particular case here, x takes on 0, 1, 2. So these are the values, and the pxx must be non-negative as we check here. Okay, and the second thing that we need to check is that let's say these values that x take on, let's say we call it s. Okay, so as to not write so much. That the sum over all possible x in S of the probability mass function must be equal to 1. Okay. Now, for the above example, we can check that the sum over x in S of Px of x is equal to what? Is equal to 1/4 plus 1/2 plus 1/4, which is equal to 1. So we are good, right? So here we have checked these two conditions, and these are the two necessary conditions for the probability mass function to be a valid probability mass function. Can you see? Okay, is this clear? All right, so this is the theory behind the probability mass function. Okay, the probability mass function is very useful because it allows us to actually compute probabilities. All right, so for example, if I want the probability that x is bigger than 0, how do I do this? All right, in this particular example, note that x can be 0, 1, or 2. So x bigger than 0 means probability of x equals to 1 plus probability of x equals to 2. This is nothing but Px of 1 plus Px of 2. So this is equal to 1/2 plus 1/4, which is equal to 3/4. Okay, so the probability mass function allows you to now look at these particular events. This is a particular event, and to compute the probability of this event. So we can actually write this as, say, this event here is x belonging to some set T. In general, probability of x belonging to some set T is basically the sum over all elements x belonging to T of the Px of x. This is the probability mass function, or PMF. Okay, so as you can see here, this is particularly simple because we can just look at the probability mass functions to compute probabilities. Okay, so here we are just collecting. This means we are just collecting all those elements that belong to T. Okay, so for example, let me give you another example right here. How about probability that x is even in the above example? So you are going to sum over all possible x's such that x is even of Px of x. Now, what are the values that x is even and x still satisfies this condition that x is equal to 1, 2, 0, 1, 2. Now, the only value that x is not even is this guy here. So we should exclude it. Okay. So this is, we are just going to collect the values of x such that Px, x takes on the value 0 and x takes on the value 2. Okay. So that is basically 1/4 plus 1/4, which is equal to 1/2. So that's another example of this particular calculation. And we can say that here we can actually replace x is even with x in T, where T is the, say, set of even numbers. So as you can see here, if you have the probability mass function, you actually have a pretty powerful object for you to compute the probabilities. Okay, is this clear? Any questions? Any questions? Okay, any questions? So now we can actually do a lot much more. Okay, so for example, now we are interested in actually computing the probability mass function for a particular random experiment. So now let's go back to this particular random experiment that we looked at just now. Okay, this particular experiment where we are rolling 2 dice and we are interested to figure out the probability mass function associated to the maximum random variable. Okay, so let's look at this particular experiment where we are rolling 2 dice, each one of 4 faces only. Okay, so this is a particular experiment in which we roll 2 4-sided dice. Okay, and we can define a particular random variable x to be the maximum of the 2 rows. Okay, so what are the values that x takes on? Well, x takes on the values belonging to 1, 2, 3, 4. Only these values are valid. Okay, because the maximum can only be 1, 2, 3, or 4. If you have two numbers from 1 to 4. So Alvin G, the left X is uppercase. Where is the left X? Where is the left X? You mean this one? This one here? Yeah, this is uppercase. All right, this is uppercase. When we talk about random variables, it is uppercase. When we talk about the values that it takes on, this is lowercase. For example, these two are lowercase. All right, and this guy here as well. Okay, and yeah, the values that little x take on, these are actually the x's that are lowercase. Yeah, if you have questions, just feel free to ask. Okay, lowercase. So this one is the random variable, must be uppercase. Okay, and this is also a random variable, is an uppercase. Now, generally my sets are also uppercase, so sometimes there's some confusion. But generally, random variables are X, Y, Z. Sometimes W. No other choices. All right. Now, if you take this class in some other semester, and Prof. Charles teaches it, right? The other professor is Prof. Charles, okay? Then his random variables are sometimes ABC. All right, but I will never use ABC for random variables, because ABC for random variables are used by quantum people, and he's a quantum person. I never use ABC. I'm a classical person. So all my random variables are X, Y, Z. At most, there's one more W. Okay. So we use the end of the alphabet for random variables, typically. Okay. Okay. Alvin G, is this clear? Generally, my capital X is going to be larger than my little x, but sometimes I don't distinguish. Okay. Right. So now we have this, we can define this random variable X here. And what are the probabilities, probability mass functions? So now, let's look at this px of little x here. This is little x. 1, 2, 3, 4. Okay. Now, what is the probability of x being 1? What are the possible outcomes that yield 1? Okay, let's look at that. Okay, sorry. Let me not try to be so fancy. Now, the only outcome that can yield 1 is this point here. Okay, and that gives a probability of 1 over 16 here, 1 over 16. And 1 over 16 comes from 1/4 times 1/4. All right. So px of 1 is equal to the probability of 1, 1 appearing in the dice row, in 2 dice rows, which is 1 over 4 times 1 over 4, which is 1 over 16. And that is this point here. Okay, so how do we get 2? All right, the only way you can get 2 is if you land here in this strip here. If you land in this strip here, oh, sorry, not here, this strip here. So in these 3 points here, this point, and this point, then your maximum will be 2. All right, and that would be 3 out of 16 here. The reason is because you have 3 outcomes that can lead to 2. Okay, so px of 2 is the probability that you get 1, 2, 2, 1, 2, 2 in 2 dice rows. And each one of these outcomes has the same probability, 1 over 16. So this is 3 times 1 over 16, which is 3 over 16. Okay, so that is the next point. This is basically how we are going to construct our probability mass function. Now, it becomes more and more complicated, but this is the region in which our maximum is 3. And how many points are there here? As you can see by careful bookkeeping here, the total number of points you have is actually 1, 2, 3, 4, 5. And that leads to 5 here. All right, and I'm not going to write down the calculation anymore. You can just count. So that is your probability mass function, okay, up to 3. Now, furthermore, the last point is basically this. Your outcome lies here. And how many realizations of the 2 coin tosses or 2 dice roll? 1, 2, 3, 4, 5, 6, 7. And that is where you get 7 out of 16. Here is 7 out of 16. So if you notice, what do you notice here? Okay, if you take, okay, now I have px of 3 is equal to 5 out of 16, and px of 4 is 7 out of 16. What do you notice? If you sum over all possible x belonging to 1, 2, 3, 4 of px of x, this can be written as sum of x running from 1 to 4 of px of x. This is nothing but 1 over 16 plus 3 over 16 plus 5 over 16 plus 7 over 16. So these values here are nothing but these values here. Can you see? All right. So what is this? 1 plus 3 plus 12 is 16. So this is 16 out of 16, which is 1. So we have to always check that our PMF adds up to 1. Otherwise, it's not a PMF. Okay. So today we learned this concept of PMF, and I want to introduce 2 more things before we call it a day. Okay, PMF stands for, sometimes we write it as little p, little m, little f as well, stands for probability mass function. And it's px of x, is this quantity here that we have been trying to evaluate. Okay, so given a particular random variable, for example, the maximum of the 2 rows, then we can create its PMF, which is this. This is the PMF. The PMF must add up to 1. Okay, and the PMF is a bunch of values here. All right, 5 out of 16, 3, 1, and 7 out of 16 must add up to 1 and must be non-negative. Okay, so why we call this probability? Because they encode the probabilities. Why we call this mass? Because these look like masses. How heavy each element is, mass. And it's a function because it takes each one of these values. Okay, px takes this particular value to a number. Anything that takes something from something in math is called a function. Okay, a function. So it's called a probability mass function. And from the random experiment, you can figure out the probability mass function. Okay, onshore you understood? Cool. So now I want to conclude by talking about 2 canonical random variables, very important discrete random variables. The first of which is called the Bernoulli random variable, and it's like this: Bernoulli random variable. Well, it is a random variable x that takes on only 2 values. So it's kind of a dumb random variable. X takes on only values 0 or 1. So x equals to 1 means that, for example, you coin toss. The coin toss is a head. All right, that could be a particular experiment that led to the random variable being a 1. And if the coin toss is a tail, then x is represented by 0. Okay, so that is the particular random variable associated to a particular experiment. And this is a proper random variable because it takes on values on the real line. Okay, so the experiment is as follows. This is your sample space, omega, and there are 2 sample points, heads and tails, and your random variable brings you from each particular outcome to a particular point, 0 or 1, and your mapping is basically the following. If you're a tail, then you go to 0, and if you're a head, you go towards 1. So that is your particular random variable x. Okay, so the formal way to write this random variable in proper mathematics is the following. Okay, so you can write this as px of k. Now this is lowercase and an integer k, and this is uppercase, which is the random variable x. Okay, we can write this as follows: p 1 minus p, where p stands for the probability, say coin toss is a head, and p is the probability of the coin toss being hit, say. Okay, then p1 minus p if k is equal to 1 and if k is equal to 0. We can write it this way. Okay, so you can check this is a particular proper random variable, and it has a probability mass function, and this probability mass function is given by this object here. Okay, so this random variable can only take on 2 values, and the 2 values are k equals to 1, k equals to 0, and basically it can be represented in this form. Now, in higher mathematics, right, and this is not in the book, if you want to copy and copy, we can actually write the Bernoulli random variable in a slightly different way, which is usually more convenient. You can write it this way: Px of k equals to p to the k, 1 minus p to the 1 minus k. Now, this form with k equals to 0 and 1 is actually the same as this form. But you can see that this is a bit strange, all right, because there are some powers here. But if you notice the following, all right, if you notice that k, let's say I put k equal to 0, then what do I get? P to the power 0, 1 minus p to the power 1 minus 0. And this is exactly 1 times 1 minus p to the power 1, which is equal to 1 minus p. And this is for k equals to 0. This part here corroborates this part. This part is the same as that part. Can you see? So this power way of writing is actually quite powerful. Let's say k is equal to 1. Then this p to the power 1, 1 minus p to the power 1 minus 1, and we are left with p times 1 minus p to the power of 0. Anything power 0 is 1. So this is p. All right. So here you see that you have this clause here. This clause is repeated here. Okay. So this representation is a valid representation as well. And sometimes it is more useful than the standard representation of this. Okay. So now, finally, I want to talk about the Bernoulli this is called the Bernoulli random variable. And now, finally, I want to talk about the binomial random variable. Binomial. As you can see, the binomial random variable seems to be related to the binomial coefficient, or n choose k. What does the binomial random variable represent? Now, a binomial random variable has two parameters. N is the number of trials, and P is the probability of success. Okay, there are two parameters. N here is an integer. P here is the probability of success, is the number between 0 and 1. Okay, and the binomial random variable actually represents the following. P of x, we can write down. No, x. X here is the number of successes in n trials. So, for example, we are going to toss a particular coin. Toss a particular coin n times, and we want to understand what is the probability that we succeed k times. Okay, so probability of x equals to k is the probability of, say, k heads in n tosses of a particular coin with probability of success p. Now, how do we get k heads in n tosses? Well, we will have to select which one. Say we have n tosses here. So these are our n tosses, and we will have, say, 3 heads. The heads must be here, 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 and then the remaining ones are tails. How many ways are there of choosing 3 heads out of 5 trials? Well, that is 5 choose 3, right? So that we have, if we want k heads out of n tosses, we generally will have this term n choose k. Okay, because you could basically, we are choosing a bunch of heads, 3 heads out of a total of 5 trials. So this is one particular configuration. We could have another configuration where the heads come later on. All right, so the head could be here instead of somewhere else. Maybe the heads could be here, here, T, here. All right, so there are 5 choose 3 such combinations altogether. Now, but for a particular head to succeed here, we will have to have p to the power k, and for a particular tail, how many failures? We have n minus k. All right, and how many heads can you have in n tosses? You can have 0 heads if you're unlucky, 1 head, 2 head, all the way to n minus n heads altogether. So this is what we call the binomial distribution. Okay, first we are going to select which of the bins here contains a head. Then for those that contain head, you need to be so lucky to have probability p. So there is a probability p here, p here, p here, and 1 minus p here, and 1 minus p here. So this part here, comes about because of multiplying these terms here. Okay, and this part here, the coefficient here, comes about because of the selection of the locations of the heads among the 3 heads in the, say, 5 bins here. So this is called a binomial random variable with a particular PMF, and the PMF is given by this particular formula. Now, clearly, because as I mentioned, PMF must add up to 1. So if I sum k running from 0 to n of this particular formula pxk, which is sum k running from 0 to n of n choose k, pk1 minus p to the power n minus k, even though this is not obvious, this is equal to 1. It must be. It must be. All right. So this is a particular random variable, which is represents the number of successes in n trials. Trials means we are trying something. All right. So here what we are trying is we are trying to get head when we toss a particular coin, and we get head with probability p. All right. And we have k heads. So basically, this is the probability that x takes on the value k. X is a particular random variable because it can only take on real valued numbers. Okay, 0, 1, 2, all the way to n. So this is a particular random variable that is called the binomial random variable. Okay, so this is where I will stop today. Next time I will move on. I will continue from here and talk about 2 more classes of random variables that you need to know, which is the geometric random variable and the Poisson random variable. For discrete, you only need to know these 4 classes of random variables: Bernoulli, binomial, geometric, and Poisson. And today you saw these 2. All right. And in homework, you convince yourself that the binomial random variable with n equals to 1 is the Bernoulli random variable. So the Bernoulli random variable is more special than the binomial random variable. Okay, so the binomial random variable with n equals to 1 is exactly the Bernoulli random variable. Okay, all right, so this is where I will stop today, and I hope. Okay, David, hypergeometric is something that I will ask in the homework, but I will not really discuss it in the lecture. You have to innovate to get to the hypergeometric. All right. I will not discuss in detail in the lecture, but it is certainly something that may be examined. Okay. For example, in the homework or one of the tutorials, you will have to play with hypergeometric. Right. Anything else I can answer? So maybe on Thursday I'll see you in the lecture theater. All right. But for now, take care and see you. Any questions? You can stay back and ask me any questions. For those who don't really want to stay back and you want to leave, you can feel free to leave. But now I'm here. I am happy to answer any question. David, you managed to hand derive it. Is it always discrete? You mean that the it refers to hypergeometric? Yeah, hypergeometric is a discrete random variable. Yeah, it's a discrete random variable. Yeah. You can go and find Wikipedia for more information. Okay. Anyone else wants to ask me any random questions? Nope. All right. So we'll call it a day now, and I'll see you. Bye-bye.